So from the review worksheet, number 15, area enclosed by is calculus code word for take an integral. Because when we take an antiderivative, that tells us the area under the curve. So I have no idea what this graph looks like, but I'm going to graph it from 0 to 2. And whatever it looks like, it probably doesn't look like that, but the area then is the integral from 0 to 2 of that function. So it's just a fancy way of asking you to take an antiderivative. And I guess making sure you know what the limits are from 0 to 2. 2x over 2x squared plus 1 dx. So what's the method on this one? Yeah, use substitution, because then du will be the top. Although it's a little bit tricky because that does look a little bit like inverse tangent down there with u squared plus a squared, except that the 2x is up there. So let's do u equals 2x squared plus 1. Du equals 4x. That's a relatively easy fix. I'll just multiply by 2 and divide by 2 to make it 4x. So 1/2 du over u. What's the integral of du over u? Natural log. So 1/2 natural log of u. And then we've kind of done them both ways today. I can change my limits to u limits and plug them in, or I could put 2x squared plus 1 back in for u and use the original x limits. Either way, I generally prefer switching the limits, so I'm going to switch the limits to u limits. So I plug in 2. Oh, careful here. 2 squared is 4, times 2 is 8, plus 1 is 9. Plug in 0. 0 plus 1 is 1. That's an easy one. So 1/2 natural log of 9 minus 1/2 natural log of 1. That is a safe stop. I'm glad you asked this question, though, because there is multiple choice answers, and this actually came up in the always exciting Facebook group on from calculus teachers. Once you become a calculus teacher, you can join the group too. Until then, you're not allowed. But this came up yesterday. It was yesterday, and it was a problem really similar to this. And one of the teachers couldn't figure out how the answer was natural log of 3. Well, there's a couple things going on. What's the natural log of 1? 0. Okay, so that part's gone. We're not worried about that. And then do you remember a property of logs about what you can do with that number? It can become the power, and then 9 to the 1/2 is the same thing as the square root of 9, which is where natural log of 3 comes in. So that would be kind of a tricky one if you got to here. And again, on your own, stop there. Like, don't even, I wouldn't simplify it any further than that. But if you start looking at multiple choices, you might think, well, where in the world did 3 come from? And you would have to use the log power. So, you still got to know your algebra. So, test outline. 826, if I remember the order right. 8 integration problems. That's like 1 through 12 on the review. Two, find the derivative problem. Suspiciously like 13 and 14 on the review. And then 6, multiple choice questions, which will be sort of like 15 through 18 on the review. And today's warm-up. Some of the warm-ups today were inspired from the multiple choice section. So the homework that's due, there's been 9 assignments. 6 of the 9 are due. Yeah, those are the ones. 334, 354, 363. Worksheet, I should have labeled that better. The first part of 372, the second part of 372. That was trig stuff. A worksheet from page 208, worksheet from page 380, and then the review worksheet. 1, 2, 3, 4, 5, 6, 7, 8, 9. There were 2 page 372s. The first one was just the trig stuff, and then the next one was derivative of trig. They were 2 different days. Oh, I remember that worksheet before that was just mixed up integral practice. Mixed antiderivative practice. So 6 of the 9. Any 6, but the review would be highly, highly, highly recommended to be included in that. But I'll let you choose. Yes, sir.
For the, I think it was the mixed integral practice.
Yes.
You had us do all of the odds up to like 31, I believe. Do you want the entire worksheet done, or just?
No, you're right. That was odds. That was odds. That's the one we spent time in class. We just took the whole day and worked together. So hopefully everyone's got that one done, because you either finished or got within 1 or 2 of finishing. And the review worksheet is kind of like that too, at least the first 12. It's just mixed up integration, which is what you need to be practicing. You know, it's one thing to go to a certain page in the book where they're all kind of the same, versus we get to the review worksheet and they're all scrambled. Can you make heads or tails of the different types of integration? Let's look at number 16. Find the area enclosed by, again, code word for take an antiderivative of this function and the x-axis. So extra sneaky, it doesn't tell us what the limits are. Let's see, 16 minus x to the 4th. I need at least a rough picture of what's going on here. If x is 0, then y is 16. If x is 1, then y is 15. If x is 2, let's see, 2 to the 4th is 16. So I'm down to 0. And because it's to the 4th, negative 2 would be the same thing. So this is like a super steep, it's not a parabola, so I shouldn't use that word, but that's roughly the shape of it, a steeper version. So when I do a quick graph, then I catch what my limits are from negative 2 to 2 of 16 minus x to the 4th dx. That would be that area. If you're paying attention and you really want to be clever, you could do limits from 0 to 2 and just multiply it by 2. Does that make it easier or harder? I don't know. It's your call. I guess I'll leave it as is. Although I think on the key I did 0 to 2. Because I was thinking ahead and thinking plugging in 0 would be easier than plugging in negative 2. 16x minus x to the 5th over 5. Yes, negative 2 to 2. I sense a safe stop in our near future. 16 times 2 minus, speaking of safe stops, 2 to the 5th over 5 minus 16 times negative 2 minus negative 2 to the 5th over 5. Safe stop. Thank you very much. I'll be done here. Although 32 plus 32 would be 64. And then minus 2 to the 5th, 32 over 5. And then minus another one, minus 64 over 5. I guess that's a little bit cleaner answer. But given the choice, safe stop. But it was a good question because it did not tell you the limits. You had to kind of graph it and figure out where it intersected the x-axis to know what to use for the limits. Complete the square, but that's jumping ahead a little bit. I don't know that. I first look at the denominator. If I'm thinking u substitution, du would be 2x minus 6. That's nowhere up there. But maybe my brain remembers that u squared plus a squared goes to inverse tangent. And so if I can get it to look like that, then it's inverse tangent. But in order to look like that, I need to complete the square in the denominator. So x squared minus 6x. Kind of set the 13 to the side. You can't get rid of it, but you can move it to the side. B over 2 be negative 3. This is the half it, square it, add it part of complete the square. Half it, square it, we get 9, and so we'll add it and make it plus 9. So now this is a perfect square. But of course I can't just stick a plus 9 in the bottom. That's not legal. I would also need to do a minus 9 in the bottom. In fact, I don't like the 5 there either, so I'm going to take that up front. And this whole chunk becomes x minus 3 squared. 13 minus 9 is 4, which is conveniently enough a perfect square. And so now this looks like inverse tangent, u squared and a squared. So u is x minus 3, and a would be 2. Du would be just dx, so I don't have to worry about messing with anything to fix that. So 5, and then the antiderivative of this is 1 over a, so 1 over 2. Inverse tangent of u over a, x minus 3 over a, plus c. So tricky one, but one that you need to be able to do on Monday.